Hey everyone, thanks for tuning in today to our Lesson 11 lecture. A couple notes on the top, you can read those in your own time, but let's just go ahead and jump right into what we're going to talk about today, which is different types of coordinates. Okay, we're going to talk about cylindrical coordinates and spherical coordinates as well. All right, let's start with spherical coordinates. And you can see here you have an R, an S, and a T. R represents the distance from the origin 0, 0, 0 to the point in XYZ space. S, we call that your zenith angle, but basically it's the angle between the positive z-axis and the line that represents R. And then T, which is called the azimuthal angle, but again, it's just the angle that represents the space between the positive x-axis and the vertical line from the point down to the xy plane. Okay? You can see over here are the spherical coordinates. X is going to be written as r cosine t sine s, y is written as r sine t sine s, and z is r cosine s, which you've already probably learned from your triads. All right, so if we want to graph the sphere, x squared plus y squared plus z squared equals 25, what do we set for r, s, and t? Okay, well, r, it's pretty basic. That's just going to be 5 because the radius is 5. Now, if we want to fill in the sphere, then we let r range from 0 to 5. But if we're just graphing the sphere itself, then just 5. Okay, then s will go from 0 to pi, and t will go from 0 to 2 pi. So a couple questions about this here. What if we restrict s to 0 to pi over 2? All right, so think about that here. Remember, this is s right here. 0 to pi would be that, but if we just went 0 to pi over 2, that would just give us the top half of the sphere. All right, what if we let s go from 0 to 2 pi? So, yeah, that would give us 0 to pi, which would give us our full sphere if we spin it around, but it'd also give us this half over here, which if we're spinning that around again, we're going to end up tracing out 2 spheres. All right, what if t went from 0 to pi over 2? Remember, t is right here, right? So 0 to pi over 2 would just be this chunk right here. Instead of going all the way around, it's going to be this chunk right here. So we're going to get, for that, we're going to get a quarter sphere. I don't know if there's a fancy name for that. We'll just call it a quarter sphere. What if we let r range from 1 to 2? Well, in that case, we're going to get a hollow sphere whose inside radius is 1 and whose outside radius is 2. All right, separate question here. What if we let r vary, but we hold s steady at pi over 3, but that we let t go all the way around from 0 to 2 pi? So the key here is that s is steady. All right, so s is steady at pi over 3. So that is going to make this a cone. Okay, and you can see here, that's what that picture would look like. Okay, so s being pi over 3, that's so that this angle between the positive x-axis and our line there is going to be held steady at pi over 3. And we're just going to spin that around, and as it spins around, it's going to make a cone. All right, so next question here says, what makes the equation of a sphere different from an ellipsoid? All right, so the equation of a sphere we know as x squared plus y squared plus z squared equals r squared, whatever that radius would be. So how is that different from an ellipsoid? Well, just like an ellipse in 2D, x would turn into something like, x over a, and then y would be y over b, and then z over c equals some number d squared. Okay, because it doesn't have one radius, it has multiple radii. So that's why we'd have no radius at the end there, just some number d, which for an ellipse we always wanted to keep at 1 if possible. The volume conversion factor, which you can prove using the volume conversion factor or the area conversion factor formulas that we learned previously. But the volume conversion factor from Cartesian to spherical, it's always going to be the same. It's the absolute value of r squared sine s. However, we generally keep s from 0 to pi, so we really don't need those absolute value bars. Because if you take the sine of every angle from 0 to pi, you're going to get a positive number. And if you square r, you're going to get a positive number. And a positive number times a positive number will, of course, give you a positive number. So the absolute value bars are pretty obsolete there, unless we change our domain of s. Last thing on this page, how do we determine whether an object sinks or floats? Well, just like in, you've probably taught this in other classes before, you look at the density. All right, you want to think about its average density. Is the average density greater than or less than the density of the medium density? All right, so more dense objects will sink, less dense objects will float. So I'm going to take a look at cylindrical coordinates. So here's a picture of cylindrical coordinates. This one might be a little bit easier to visualize. R is just the distance on the xy plane from the origin to the point directly below or above the point. S is our vertical distance, so basically it's our z coordinate essentially. And then t is our angle between the positive x-axis and the shadow of the line from the origin to the point. All right, so you can see over here our cylindrical coordinates. X will be our cosine of t, y would be our sine of t, and z would be s. So here is a look at finding volumes of various shapes in cylindrical and spherical coordinates. Let's talk about a cone where s is held at pi over 3. We'll let t vary from 0 to 2 pi and r vary from 0 to 4. Okay, first let's take a look over here at what this picture looks like. So you can see the picture ranging from 0 to 4. S is held steady as we go around the circle. S is pi over 3, which means, this is a 60 degree, which is how I found this to be 2 and this to be 2 root 3. It's a 30, 60, 90 triangle. Right? So this over here would be 30 in a 30, 60, 90 triangle. We know that the shorter leg is half the hypotenuse and the longer leg is half the hypotenuse times the square root of 3. All right, and then you can set up a little equation here, the cosine of that s angle. So s is obviously going to be changing a little bit here, so we 2 over r. And then r would be 2 over cosine of s if we did some maneuvering there, which 2 over cosine is the same thing as writing 2 times secant. All right, so setting up this triple integral here, remember the conversion factor is r squared sine s. If you look at cylindrical or spherical coordinates, we're going to let t range from 0 to 2 pi. We're going to let s range from 0 to pi over 3 because we're trying to talk about the volume here. So it's not, even though s is being held steady at pi over 3, we want everything inside that cone as well, which is why we let s range from 0 to pi over 3. And then r is going to range from 0 to 2 secant s. All right, if we want to take a look at that in cylindrical coordinates here, the ratio r to s, as we learned in the last problem over here, is going to be 2 root 3 to 2, or in other words, root 3 to 1, right? So if we do some cross multiplying there, we would get r is equal to s root 3. So then we can set up the equation. We're going to have t, not the equation, sorry, the integral. We're going to have t range from 0 to 2 pi again. S is going to go from 0 to 2, because remember, s is just basically like your z coordinate, and that's going to go from 0 and then up to 2. And then our radius will range from 0 to s root 3. Okay, as s increases, and so will the radius as well. Okay, next one here we have a cylinder, x squared plus y squared equals 9, inside of a sphere of radius 4, centered at the origin. We want to think about how would we find the volume of this. All right, so first thing we probably got to do is figure out what the intersection points are of this cylinder and the sphere. So the cylinder is x squared plus y squared plus 9. The sphere is x squared plus y squared plus z squared equals r squared. So that would be 16. All right, pretty simple to do here. If we just multiply this top equation by -1, that would give us, when we add these together, z squared equals 7. So z equals plus or minus root 7. And since z equals s, that means s equals plus or minus root 7. All right, so now we have, if we take this equation of the sphere again, remember, x squared plus y squared in 2D is just your r squared, and z squared, since z is s squared. So r squared would then equal 16 minus s squared. In other words, r equals square root, plus or minus square root, 16 minus s squared. So now we can set up our triple integral. We're going to let t go from 0 to 2 pi. We're going to let s range from negative root 7 to positive root 7. And we're going to let the radius, the r of this shape, whatever this shape is, it's going to start at 3, right? Because if we go back over here, the radius would be 3. So it's going to start at 3, and it's going to go out to positive root 16 minus s squared. Okay? And I don't think I talked about this before, but the volume conversion factor into spherical coordinates, I already used it here once. The volume conversion factor into spherical coordinates, in the cylindrical coordinates is just r. So this is just going to be r, and then dr, ds, dt. We're not going to walk through solving that. It can get a little tricky without having Mathematica at our disposal. But that would be the setup for it. All right, the last thing I want to talk about here with you is just this last problem here. That's basically what we're doing. We're finding the volume of like a chord out sphere. Okay, that's kind of what's going on here. Now, you probably did something like this in your geometry class. And, you know, if you had all the measurements, doing this in geometry would actually be very easy to do. Just take the volume of the sphere and the volume of the cylinder, and you can do some subtraction. However, there's only going to be a little piece of the top and the bottom that you'd be missing if you did that. Okay, so there'd be a little bit more work involved in that. This method takes care of all the missing cylinder in the middle. All right, that'll do it for our lesson 11 lecture. As always, any questions, just let me know. Thanks for tuning in.